Today's lecture is on density. This is the fifth lecture of the first module on principles of oceanography. Density, we're going to talk about density in the context of oceanography, but it's not different than the normal density you're used to from chemistry or physics. Density is the amount of mass per unit volume of something, usually described as grams per cubic centimeter. The density of fresh water is 1 gram per cubic centimeter at 4 degrees C, which is nice and easy to remember. But the density of seawater is a little bit different than the density of fresh water, and that actually drives all sorts of things in the ocean. First, before we talk about the influence of salts, I want to talk about the unique feature of how water acts with density. And this, again, gets back to the previous lecture about why water is so special and doesn't act like other things that it should act like. So if you start here at liquid water at 20 degrees C, and then we're going to move to the left, you can see the water molecules sort of floating around. Nothing very exciting happening. This is the density here in grams per cubic centimeter, about 0.9982. And so then you lower the temperature, so you move towards 15 degrees, and the water molecules start to compress a little bit, and they start to get a little bit closer together. And as that happens, density rises to point B, and then you cool it off even more. You get to 4 degrees Celsius, and now you've really compressed things. So you still have liquid water molecules, but things are definitely a little bit denser. Your density has gone up again to now here's point C, a density of about 1. And then this is where water behaves differently. So on this bottom chart, the green line shows you what sort of normal, quote unquote, normal compounds do. As it gets colder and colder, and so your temperature is going down this way, density in this green line rises and rises and rises until when it becomes a solid, you end up with the maximum density, which means that this solid of whatever this green compound is would sink if you put it in a vial of the liquid green compound. But water behaves differently. What happens between 4 degrees and 2 degrees is that as water starts to freeze, the hydrogen bonds start to align themselves in a really regular way. And so you actually end up with something that starts to become less dense. And you can see if you just look at the number of molecules in this box versus the number of molecules in this box, you can already see that that compressibility is already starting to loosen up a little bit. And they're starting to arrange themselves in a pattern. So from 4 degrees to when you start really almost forming ice at 2 degrees, the density goes down. And then when you form ice, you get this lovely hexagonal crystalline structure. And it takes up a lot more space. It leaves a lot of space, a lot less molecules there. And so the density actually dramatically drops. So ice is significantly less, freshwater ice is significantly less dense than the water around it, which means in this case, the solid actually floats. And I mentioned this before, that this is really important because what it means is when you form ice on a lake or in the ocean, it floats on the surface. It doesn't drop to the bottom. And if it dropped to the bottom, like any other sort of normal compound would, you'd end up with it keep forming ice on the surface, and it drops, form ice, and it drops, and next thing you know, you've got a body of water that's completely frozen solid. And this is something that you guys have probably more intuition than you're used to of. If any of you have seen snow on TV, even if not in person, you know that we think of snowflakes as having this really pretty sort of crystalline structure. And this hexagonal crystalline structure of snow is actually mimicking what the internal structure of water looks like at a molecular level. And so this is partially why the density of water increases as temperature decreases. Sorry, let me back that up. So in liquid water, the density of water increases as temperature decreases. And that's because of thermal contraction, where you saw those molecules getting closer together. Once you start forming a solid, then the density decreases again. Okay. The other thing, so this is what I wanted to show you guys. So you might have a little bit of intuition for this if you've ever stuck a bottle of water or a Coke in the freezer to cool it off really quickly. You might have ended up with a broken bottle or something that exploded. And that's because the ice that is formed, whatever it is, whatever kind of ice is formed, the water takes up more space. That very regular hexagonal crystal structure takes up a lot more space than those little liquid molecules just sort of bumping around. And so it gets bigger, and next thing you know, your bottle has broken. But of course, when the ocean, we're not talking about pure fresh water, we're talking about salt water. And the other thing about the ocean is not all the water is at the surface. Some of it is at the bottom of the ocean. And so we have to think about the impacts of increasing pressure. So that means what happens when you're at the bottom of the ocean, and the impact of adding salts. So both of these, adding pressure and adding salts, decreases the maximum density temperature. So what that means is dissolved solids or salts reduce the freezing point of water. So this is why seawater doesn't freeze as often as you might think, like at the poles, why it isn't just, completely ice covered. And it's because it's salty. So freshwater density is 1 gram per centimeter cubed. And figuring out the density of seawater requires knowing the temperature of the seawater, the salinity, so how much salts, and the pressure, so whether it's at the surface or whether it's somewhere deeper. And the differences in density are really small. It's a few parts in 100,000. But these small density differences are really important for a lot of oceanic processes. The other interesting thing about density is you can't measure it directly, and we'll talk about that in a little bit. But just to give you an idea, ocean surface water ranges from 1.022 to 1.030 gram per centimeter cubed. So that's a pretty small range. Because these numbers are so small, we tend to talk about them as kilograms per meter cubed because it's just a bit easier. So in that, it's 1,022 to 1,030 kilograms per meter cubed. And the density of water is what controls the sort of what we call the layered ocean. So things to remember, density increases as water gets colder. So colder waters are more dense. And it turns out when we look at the 3 different things that influence density, temperature is the most important. Water gets more dense as you add salts to it. And water gets more dense as you increase the pressure. So of course, and I've got a note here, this doesn't matter at the surface because there's no pressure, but when you're thinking about the deep ocean, you have to think about this. And we've already introduced the idea of a thermocline and a halocline. So thermocline being a region that in the ocean water column that abruptly changes temperature with depth. Halocline is an abrupt change of salinity with depth and keeping up the pattern. The pycnocline, which is what you call this here, is an abrupt change of density with depth. A couple of important things about density, and this will matter when you guys are getting to your practical assignments and your tests and things. Density is described by this Greek letter rho, R-H-O. The units we typically use in oceanography are kilogram per meter cubed. And in rho density, which would be like a value like this, the values change very little. And so to make it easier to talk about, we tend to get rid of the 1,000. So you take the rho value and minus 1,000, and that gives you what we call the sigma value. This is the letter for the symbol for the Greek letter sigma. So if the rho is 1,026.40 kilograms per meter cubed, then to get the sigma, we subtract 1,000. And so for that water parcel, it would have a sigma value equal to 26.4 kilograms per meter cubed. And of course, the units remain the same here. Okay, so on the left, we have the thermocline. This is a temperature profile of a particular sort of generic place in the low latitude ocean as a function of depth. So you've got your warm surface waters here, and then you've got this surface mix layer. So this is this little tiny well mix layer in the surface, and then this rapid temperature change is your thermocline, and then you've got your deeper, colder waters. So if we look to the right, we can draw a density profile for this exact same place in the ocean. And you can see that warm water means that there's less dense water at the surface, that's here. The density of all the water in the surface mix layer is basically the same because it's well mixed. And then you've got this rapid increase in density that corresponds with the rapid decline in temperature. And so that's your pycnocline, and then you've got your denser water throughout the water column all the way to the bottom. And this is good because this means that this is what we call a stable water column. So the least dense water is at the top, and then the density increases as you go down. So there's no reason for this water mass to mix. Okay, so if we move to the low latitudes, on the left we've got the temperature profile with depth, and the high latitudes are isothermal. Isothermal, meaning basically it doesn't change, the temperature is the same all the way down. And if you look on the right, the density profile mimics that. Okay, so because temperature is such a strong driver of density, your density profiles are frequently going to mimic your temperature profiles. So density then is is essentially a straight line, which we call isopycnal. And there's no pycnocline or thermocline because there's no rapid change. You know, there's no sort of area where the surface looks different or area where things are changing a lot. So we refer to this as the layered ocean, and it's driven by density. So typically in the ocean, there's 3 distinct water masses if you think about going from the surface to deep. So you have your small mixed surface layer, known as the mixed layer, and that's above the thermocline. You have your upper water, which is where the thermocline and pycnocline exist, and then you have your deep water, which is pretty much everything below the thermocline and pycnocline all the way to the ocean floor. And this will become really important later when we get to circulation and water masses and learning to identify different water masses of the ocean and understanding how ocean water circulates. And again, to say the high latitude ocean, so this is the Arctic and the Southern Ocean, you very rarely have a thermocline or a pycnocline. And in this case, these are known as isothermal and isopycnal, so meaning that there's no temperature variation and no density variation in the water column. Here you can see this is one of these cross-section plots that we introduced, I think, with the temperature lecture. So this is a temperature profile of the Atlantic Ocean. And remember I said to start by finding whatever this little box is that will tell you where in the ocean you are. So this is the Atlantic Ocean because I can see Africa and South America and North America. And this is a transect going from the North Atlantic all the way down to the South Atlantic. So here is equivalent to here. And then as you move down this line, you're moving this way till you get to essentially the Southern Ocean. And what this plot is showing you is what the water looks like along that line from the surface all the way down to 6,000 meters at the very bottom. So if we look in the Southern Ocean, you can see very nicely, if we were to draw a temperature versus depth profile, it would go from essentially 1 degree to 0 degrees. So that's pretty close to isothermal. You can see this really cold water, blue water up here at the surface. Whereas we go to the equator or even 20 degrees north, you can see you've got really warm waters at the surface. So 20, 15 degrees, 10 degrees. And then now you've pretty much hit your thermocline where you've got this rapid change where all of a sudden it gets cold. And then you've got your deep waters, which stay very cold. So these changes in temperature with depth are going to have a big impact on the density of these waters. But salinity is also going to play a role. Salinity definitely impacts density, and there are some parts of the world where salinity can become even more important than temperature. And so both of these, the temperature and the salinity, are going to be impacting what the final density is. So temperature and salinity work together to influence density. And so we use temperature and salinity to create what we call TS diagrams. And you'll see these a lot in oceanography, so it's worth spending some time taking a look at them. So this is a plot where on the y-axis you have temperature, and the x-axis you have salinity. Okay, and so what it's showing you is for any given water, what the density of that water is for temperature, for a given temperature and salinity. And these values are in 22, 24, 26, 28, which means these are sigma values, and they're in kilograms per meter cubed. But the question is, which one of these TS diagrams on the right is actually correct? So if you think about it, so what happens when temperature gets colder? So temperature goes down. All right, what does density do? Well, when waters get colder, you have this contraction where they start to sort of squirm together more and the liquid molecules start compressing. And so what that means is that density actually increases. Okay, so we need to find a plot where as temperature declines, density increases. So let's see, if we take a temperature value here on the first plot, temperature goes down. You can see you go from a density of 22, 24, 26. Okay, so density 27. So in this case, that's fine. Density's getting higher as temperature goes down. If we look at this second plot here, and we go for a given temperature and we look all the way down. So here, as you get colder, density is actually getting lower, 28, 26, 24, 22. So this plot can't be right, okay? Because density isn't doing what it's supposed to do with temperature. This one, for a given temperature as you move down, density is getting higher, so that's fine. And then this one here, as temperature goes down, density is getting lower again, just like this plot on the left. So this plot can't be real, okay? So we're left with the top two as possibilities. Let me see if I can, whoops. I didn't mean to do that, obviously. Oh, shoot. Oh no, that's not what I wanted to do either. Okay, starting over, sorry about that. This is actually perfect. Okay, so we had these two as possibilities and these two not as possibilities. Okay, so salinity, as salinity increases, you end up with more salts, so more stuff in a given parcel of water. So that means as salinity increases, density also increases. And so to check these plots, what you want to look at is you want to start here and say, all right, as salinity increases, what happens to density? Well, you can see you go from 25, 26, 27, 28. So that's correct. Whereas in this plot, if you have a given salinity and you increase salinity here, so temperature is doing what it's supposed to, but here density is going down as you add salinity. So this is not true. So this is essentially the shape that a TS plot will always make. Okay, you should always see lines that move like this. All right, so salinity and temperature impact density. So let's just look at them on their own briefly. And so on the top left, what we're looking at is if you hold salinity constant, you can see that as temperature goes down, okay, as you get colder, density goes up. So that's good, that's what you'd expect. And on the bottom right, if you hold temperature constant, what you can see here is that as salinity increases, density increases. Okay, so you can see what we looked at in the previous slide was temperature and salinity at the same time. Here we're looking at temperature and salinity separately. Okay, so how do we know the density of a water parcel? Well, we don't have an instrument that goes out and measures density. What we can do is measure temperature and salinity and then also determine the pressure of the water. And this equation of state is how we then basically calculate density empirically. And so what was done was a whole ton of laboratory measurements from around the world covering a variety of salinities. And people came up with this, basically this like crazy empirical relationship, meaning that they looked at the relationship between temperature, salinity, pressure, and density and came up with this crazy equation so that if you know the temperature, salinity, and pressure, you can use it to calculate density. Well, of course, nobody wants to actually be doing this math. And so that's where that TEOS 10 site that I was telling you about comes in. Basically does it for you, which is really cool. Okay. So this, again, is getting to what I said before with units. The absolute density isn't super useful because these small density differences are really important. So if you have a rho value, you convert it to a sigma value. And that gives you a way to look at small changes like we did with the temperature salinity diagram. And these TS diagrams are really useful. So it allows you to look at different water masses, and mixing between them and their geographical distribution. And I'm not going to go into this at all because when you guys get to circulation, you're going to talk about this a lot. I just wanted to sort of give you a taste of how these things are all related. So this is, instead of an idealized temperature salinity diagram, this is a temperature and salinity diagram with a bunch of data plotted on it. So you've got your salinity here on the x-axis, temperature on the y-axis, and all these black crosses are sort of data that was collected from various parts of the ocean. And it's useful to look at this because what you can see is that, for example, like the surface waters up here have to be less dense because if they were more dense than the underlying water, they would sink. But the fact that they're not sinking and they're staying at the surface means they have to be less dense. And you can see that here with the temperature and salinity values measured for surface water. And then as you go down, the waters with the highest density occur here. So they're between, it looks like 27 something and 28 kilograms per meter cubed. And these are your bottom waters. So they have your coldest temperatures, in this case, your lowest salinities, but it doesn't matter because they're so cold. And it's good. They're staying at the bottom because they're the most dense. If they weren't as dense as the water above them, then they would rise. They would float up. And the other cool thing you can do with temperature salinity diagrams is, look, so this water is actually in different places, but because it's all on the same, falls on the same density line, it means it can mix. And if you have water, let's say sort of moving through the ocean, and it encounters a second body of water of the same density, then those can mix. Okay? If you have a water parcel moving through the ocean, and it encounters a body of water that is lighter than it, so less dense, this water will sink underneath it. And they're not going to mix. All right? You're going to end up with two distinct layers, as if you had like oil and vinegar in your salad dressing. Okay, so again, looking at a temperature salinity diagram here, where these lines, these black lines are showing you the density values, so 27.5 kilograms per meter cubed all the way through. You can see these curved lines, and the thing with these lines is they're not linear, so they're not straight lines. All right, so temperature and salinity have what we call a slightly nonlinear effect on the density of seawater. And this becomes interesting because if you take two water masses, all right, let's say you have a place in the ocean where you go out and measure water, we'll label it place L, and it has a particular temperature and salinity. So let's say it has a temperature of, that looks like 3 degrees C, and a salinity of, I don't know, 33.3. And you say, okay, cool, that water then, with that temperature and salinity, it has a density of 26.5 kilograms per meter cubed. Awesome. You go out and you measure a different part of the ocean, part G, and that has a temperature of, I don't know, let's say 11 degrees C and a salinity of maybe 35. Cool, so it also has a density of 26.5. Okay, so these two parcels of water, very different temperatures, very different salinities, but the same density. So if they encountered one another, they would mix. Awesome, not a problem. Here's where it gets crazy. If you took these two water parcels and you mix them together, so you make a new water, so let's say you grabbed a bucket of L and a bucket of G, and you stuck it in a third bucket called M, and you mix these two up, the temperature would be the average of G and L, so the average of 3 and 11, which is 7, which it looks like exactly that's what that is. And the salinity would be an average of 33.3 and 35, which it looks like it is, roughly 34.1. Okay? So that's because temperature and salinity mix conservatively. They mix linearly. But as you can see here, a water mass with an average temperature of 7 and a salinity of 34.1 does not have the same density as the water it was formed from. It actually has a higher density. It's moved away here. So let's say it's got a density of 26.6. And this will always happen. And it's really interesting. And it has to do with the way, the fact that there's this nonlinearity in these relationships. And so it's just something to keep in mind, that if you're asked, you know, if you're mixing parcels of water and you say, what's the new density? You can't just take the average of the original two densities. You actually have to look at a TS plot and find what the density is based on these lines. And these lines have been determined from that TOS 10 big equation that I showed you before. All right, so that's it on density. And the temperature, salinity, and density